To close, we now consider example 3, a truss shown that's part of a hoist. The cable segments are horizontal and vertical, and we want to determine the support reactions and the force supported by each member of the truss. We might also note that members AC, CE, BD, and DF are all horizontal, that AB, CD, and EF are vertical. That simplification in geometry will help us with some aspects of this problem. So here we have a truss with 9 members and 6 joints, and the loads are applied to the truss through the pulley mounted at E. Before we do anything else, we should make some notes about important features of this problem, then plot a strategy for finding the information we want with the least amount of effort. We can see from the supports that the truss is statically determinate with a pin support at A and a roller support at B, so finding reactions at A and B seems like a good way to start. Note that we can either leave the pulley on the truss or take it off and replace the pulley with the forces its bearings exert on the truss at E. I'll choose to remove the pulley, but I'll come back to that after we've discussed some other features. Note that joints A and E are connections between two mutually orthogonal members, AB and AC at A and EC and EF at E. Once we apply the bearing forces at E and find the reactions at A, we'll immediately know the forces in the 4 members AB, AC, EC, and EF. Note also that we have a zero force member in CD based on joint equilibrium at D. This also tells us that the load carried by BD is the same as the load carried by DF. Given these features, an efficient way of determining all member forces is as follows. We'll first remove the pulley from the truss based on this free body diagram and determine bearing forces exerted on the truss at E. We'll then take a look at equilibrium of joint E That perhaps is a little bit confusing, but when I've drawn that blue circle around joint E, the pulley has already been removed, so we'll be looking at just a free body diagram involving member forces EF and EC and whatever forces the pulley bearing exerts on the truss at E. Equilibrium of joint E will immediately provide forces in members EC and EF because of the mutually orthogonal nature of those two members. Then we can go back and impose equilibrium on the whole truss, finding reactions at A and B. So now our isolating surface for the whole truss will look like this. Again, what will be happening at joint E is that the forces from the bearing, from the pulley bearing, will be exerted on the truss at E. And we'll also then simply have the reaction forces at A and B from the pin and roller. Once we've found these reactions, we can isolate joint A. And again, the mutually orthogonal nature of AC and AB will allow us to determine the forces in those members very quickly. Then we'll go down and impose equilibrium on joint B. At this point, we'll have the force in member AB from examining joint A, and our unknowns will be the forces in members BC and BD. Once we determine those, we know that given this zero force member here, the force carried by DF is the same as the force carried by BD, so we can then proceed to joint F to solve for the force in member CF. At this point, we will have one unknown, so it will turn out we can use horizontal equilibrium to solve for the force in member CF. And then we can use vertical equilibrium as a check on the accuracy of what we've done so far. So altogether here, you'll see that we've got a total of 1, is the free body diagram for the pulley. 2 is the free body diagram for joint E. 3 is the free body diagram for the whole truss. 4 is the free body diagram for joint A. 5 is the free body diagram for joint B. And 6 is the free body diagram for joint F. The geometry of this problem will make the analysis of this relatively simple, but it's a significant number of free body diagrams to get all the information we need in the problem. Our pulley is assumed mounted on frictionless bearings, so the only resistance that's offered by the bearing is to translation. There's no resistance to rotation, and we will have reaction forces here at the bearing center of Ex and Ey. We're also cutting through the cables, the vertical and horizontal cables, so we'll have, at these locations, we'll have a 6 kip load here, and a 6 kip load here. Note that even though the pulley has size, moment equilibrium is automatically satisfied. The top horizontal cable force is exerting a counterclockwise or positive moment about E. The radius of the pulley is 6 inches or half a foot, so there's a 3 kip foot positive moment exerted about E by the top horizontal force, and there is a clockwise or negative 3 kip foot moment exerted by the vertical force. So the net sum is 0, and this is already in moment equilibrium. So even though it has size, we don't have to worry about moment equilibrium in this case because it's automatically satisfied given the frictionless nature of the pulley and the bearings. So this just leaves us with force equilibrium equations, and here they're very simple. We can see that we're going to have Ex minus 6 kip is 0 in the x direction, and Ey minus 6 kip is 0 in the y direction, and that's simply going to give us Ex is Ey is 6 kip. Okay, so now we are looking at the joint at E. We've removed the pulley, and so our second free body diagram here is for the joint at E, and we'll have equal and opposite forces to those experienced by the pulley bearing. So in this case, the pulley bearing is exerting forces on the truss that are equal and opposite to what we found exerted on the pulley bearing. So what we'll have now is, since Ex is to the right on the pulley bearing, we'll have a 6 kip load this way from the pulley bearing on the truss, and we'll have a 6 kip load this way. Now, for now, I'm going to continue to follow my sign convention of drawing all the member forces as tensile, even though you may very well be able to see that the forces that the member carries are actually going to go in the other direction here. So this is the force carried by EF, and this is the force carried by EC. And again, using our standard XY coordinate system, our equilibrium equations in X will be minus FEC minus 6 is 0, and in Y it'll be minus FEF minus 6 kip is 0. And in both cases we're going to get that FEC is equal to FEF is minus 6 kip. Now, we'll just pause here and say that sometimes it is useful to represent the results this way, or we can say that this is 6 kip, and just in parentheses we'll indicate whether something is in tension or compression. So either representation here works. Both convey the fact that these two members are going to be in compression, and it's really up to you to decide what is most convenient or most clear from your perspective. Okay, so now we're prepared to take a look at the equilibrium of the whole truss, and so this is going to be free body diagram 3, based again on the big red boundary that we have up there. And in this case, it's not necessary for us to include any of the details of the truss structure. Those are all internal to the enveloping surface. So we can do this. Again, what's exerted out here at the end of the truss are the forces exerted by the pulley bearing on the truss. So they look like just as they do for our second free body diagram of joint E. So we'll have, again, a 6 kip load this way, and a 6 kip load this way. And then we have our reactions at A. We have a pin at A, so we'll have AX and AY. And we have a roller at B, so I'll just draw that as B. The truss as a whole is once again something that has size, so we're going to have to add moment equilibrium to force equilibrium, and I'll choose to take moments about A. Here we have just two contributions. We have a positive or counterclockwise contribution from the roller support B through a distance of 3 feet. So this is B times 3 feet. And then of the two 6 kip loads on the upper right, only the vertical load contributes a moment about A because the line of action of the horizontal 6 kip load goes through A. The vertical 6 kip load exerts a clockwise or negative moment about A through a distance of 8 feet. So we have minus 6 kip times 8 feet is 0. And we'll solve for B, and we end up with B is equal to 16 kip. Force equilibrium in X tells us that we have AX plus B minus 6 kip is 0. And since we found that B is 16 kip, we can substitute that in and find that AX is minus 10 kip. Vertical equilibrium here is very simple because we just have AY minus 6 kip equals 0. So I'll just go ahead and write AY is equal to 6 kip. Having found these reactions now, we can proceed to free body diagram 4 involving joint A. And we have our reactions here. We have, since we're looking at our members here, I'm going to just slide my reaction forces along their lines of action appropriately so my figure doesn't get too cluttered. We have AX is minus 10 kip, and I will leave that alone. But I will slide AY up, since that's equal to 6 kip, put it here. And again, I'll follow my sign convention of drawing the member forces as positive and let the algebra tell me whether or not that's correct. So we have here forces in members AC and AB. And again, the geometry of this particular member makes this very simple. Using my traditional XY coordinate system, I have FAC plus minus 10 kip is 0. And in the vertical direction, I have 6 kip minus FAB is 0. So in this case, both AC and AB are carrying positive loads, which means they are in fact in tension. So FAC is 10 kip and FAB is 6 kip. Okay, or we'll just say here, we could also represent this as just saying this is a 10 kip in tension and 6 kip in tension. Okay, so now we've got essentially 5 of our 9 truss member loads. If we scroll up here for just a second, we have that EC and EF were both carrying 6 kip loads in compression. We have that AC is carrying a 10 kip load in tension, AB is carrying a 6 kip load in tension, and we know that CD is a zero force member. So we have 4 members left to examine. Actually, that's not quite right, because we said that the load carried by DF would be the same as the load carried by BD, again by virtue of the equilibrium of joint D, and so we don't have quite that much to determine yet. But we'll begin now by going to our 5th free body diagram for joint B. And here we have three members. We have our 16 kip reaction at roller B. We now know FAB. We know that that's 6 kips, so I'll go ahead and represent that here as 6 kips. We don't know the force carried by member BD, and we don't know the force carried by member BC. I'm going to label this angle here theta, but note that we don't actually need to know theta because we're given information in the problem statement that this is a 3, 4, triangle. So I don't actually need to solve for theta. I can say by looking at that schematic that cosine theta is 4/5 and sine theta is 3/5. So we'll just use that directly in our problem. Okay, again, using our conventional xy coordinate system, I can write sum of the forces in y equals 0, and I have 6 kip plus FBC sine theta, and sine theta is 3/5, so plus 3/5 FBC is 0. And that just gives us FBC is minus 10 kip, or again, I'll say I could write this as 10 kip in compression. Equilibrium in X will give me FBD plus FBC cosine theta. Again, cosine theta is 4/5, so this is plus 4/5 FBC plus 16 kip is 0. So we determined that FBC is minus 10 kip, 4/5 of minus 10 is minus 8, and solving for FBD, I get that FBD is minus 8 kip or that it's 8 kip in compression. Okay, so we'll just make use of our zero force member result now to say that equilibrium in the collinear direction gives us that the force that's carried by dF is equal to the force that's carried by BD, and that again is going to be minus 8 kip. At this point, the only information we don't have is the force carried by member CF. So we'll proceed to our last free body diagram here at joint F. And I'm going to do something just a little bit different with this last free body diagram. I'll first make a note here that this angle theta is the same angle that we had for free body diagram 5. So it's again a 3, 4, 5 triangle. The sine of theta will be 3/5, the cosine 4/5. Now I could continue to follow my sign convention here and say that the force carried by dF is minus 8 kip here, and the force carried by member EF is in compression minus 6 kips here, and then I'm looking for my force carried by CF. Now that's perfectly fine, and I can proceed that way. If I write my equations using my conventional xy coordinate system, what I'm going to get in the x direction is minus a minus 8 kip minus FCF cosine theta is 0, and in y I'm going to get FCF sine theta plus minus 6 kip is 0. And that's perfectly fine. all the minus signs are a bit unwieldy, so at some point you might find that it's better to simply draw the compressive forces pushing into the joint rather than representing them as negative tensile forces. So a second way of doing this, which just might be easier for this last joint, will be to simply write this or represent this in this fashion. I'm showing this as being 8 kip in compression. That's absolutely equivalent to what we have at the left here, so I'll write this as 6 kip in compression here. And again, I'll have my FCF here. So now my conventional XY coordinate system here for my horizontal equilibrium, I'm going to be able to solve for FCF. And now I've got 8 kip minus FCF cosine theta. Again, cosine theta is 4/5. And that tells me that FCF is 10 kip or 10 kip in tension. And at this point, we're finished. Now, as a check, I haven't used vertical equilibrium, but if I've done everything consistently, this should be identically satisfied. So let's write sum of the forces in y equals 0. We have FCF sine theta, which is 3/5 FCF minus 6 kip should be 0. And what we'll do is just say, we'll put a question mark above this, equal sign. It should be automatically satisfied. So if we put 10 kip in for FCF, 3/5 of 10 is 6, so we end up with 6 minus 6 kip, and that in fact is 0. So what we've done is completely consistent all the way through. At this point, we've got our 9 member forces and our 3 reactions. And so if we wanted to, we didn't use joint C at all. That's our last joint that represents the last overlap of equilibrium. If we wanted to, we could go up and draw a free body diagram of joint C, take all this information together, write force equilibrium equations in X and Y, and verify again that those are identically satisfied as a last check on our work.